Hello and welcome to another one of D's ADD videos. Today we're going to look at the examples dealing with VESPR theory. So VESPR theory, as you know, is a good way to predict the molecular geometries of different compounds, such as this beryllium chloride. So if you were to do the Lewis structure, you would find that beryllium's in the center, chlorine's on the outside, and you would have lone pairs on these guys. Again, the peripheral elements or atoms do not matter, they're lone pairs. If you were to go to your table available on the website, you would see that there's two bonding domains. If you remember, there was no central lone pair atoms. So we know that the electron geometry is linear, and so is the molecular geometry. That occurs anytime that there are no lone pair electrons, that the molecular and the electron pair geometry will be the same thing. The bond angle will be 180. So when drawing this, it will look like that. You don't need that, and then we know the bond angle is 180 degrees. Let's look at BCl3. If you were to do that one, you would have a chlorine, a chlorine, a chlorine with boron in the middle. Everybody would get a bond. Boron's formal charge would be 0 if you did that. And then when you added the lone pairs. I've been doing this long enough to where I can do this without doing the formal steps, even though I really shouldn't. But the point of this video is VESPR theory, not Lewis structures. If you need practice with those, go watch those videos and practice those problems. So here I have 3 domains. Again, 0 lone pairs. So we should know that the molecular and the electron pair geometry are going to be the same exact thing. So 3 and 3 should be trigonal planar, and the bond angle is 120. So the way we would draw that is as follows. You write trigonal planar for both Mg and Eg. And it would look like this. Where the bond angle is 120 degrees. All right? You're starting to get the hang of it. I forgot to write linear on this one. And that's again Eg and Mg. Anytime there are no lone pairs, molecular and electron geometry are the same thing. All right, let's look at carbon tetrachloride. You will find that it will look something like this. Halogens formally single bonds. You would have let's make that one paired. That one. And that should be formal charges of 0 for everybody. And if you were to do that, you would see 4 domains. They're all bonding domains. No lone pairs. So again, we would have Mg and Eg be the same thing. And in this case, it would be tetrahedral. And our bond angle would be 109.5. And that's something you have to memorize. Anytime we have tetrahedral, the bond angle right there is 109.5. All right? Hope you're getting the hang of this. Let's do one more of the basic rounds. They get a lot more complex. Ammonia once you do the Lewis structure, you should end up with this. And here we have our first example of lone pairs. Now, the way you should look at that is you should say it's 4 domains. They're broken up into 3 bonding domains, meaning that there's the hydrogen atom on each of the bonds. And then there's 1 lone pair up top. So that means the electron geometry will differ for the first time from the molecular geometry. The electron pair geometry is going to be tetrahedral because there's 4 domains. The molecular geometry is going to be, let's look it up. Come over here to our table. 4, 3, 1. Trigonal pyramidal. Sorry about that. So the normal bond angle was 109.5, and the lone pair, however, the way it works, will take that bond angle and decrease it a little bit. So we would have 1 coming out at you, 1 going back into the page. Actually, let's put that one on this side. By convention, have it going back into the page back here. And then there's this one right here. So normally these bond angles would be 109.5. But what happens is this lone pair that has a big old electron density cloud will push these down. Technically, I should bend that line a little bit. It's a little bit more than 90 degrees, right? So this bond angle would be less than 109.5, and so would the other one on the other side. There should be an H right there, sorry. All right, so I hope I've cleared up any doubts over the basics of VESPR theory. If you practice this enough, you'll see there's not too much to it. And then once you know this, hybridization is next, and you will see that there's an easy way to memorize the hybridization based off the VESPR theory. Now, it's good to go ahead and understand the concept behind it and the process of finding the hybridization, but once you know your VESPR, you can also know your hybridization pretty easily. So practice, practice, practice. Check out the more advanced VESPR theory video examples, and thank you and have a nice day.